In this part, we will talk about the molecular shape, the geometry, and the shape of the molecule. And this is called the VASPER model. VASPER is the abbreviation of the valence shell electron pair repulsion model. So, in order to know, we want to know two things here. We want to figure out the shape and the geometry of the molecule. In order to know this, we need to start from the lowest structure. So the lowest structure is the most important thing in there. You have to get your valence electrons, draw your lowest structure. Once you draw your lowest structure, you have to calculate what we call static number. So what is static number? Static number is the total number of electron pair. Another name for it is an electron domain. And it's simply the number of atoms bonded to the central plus the lone pair. This is it. Okay, so you look at the atoms that are bonded to the central, you count them plus the lone pair. Let's have an example. Carbon dioxide. We did this example before. We found its valence electrons and then we drew its lowest structure. Now, the question here is go ahead and find the molecular geometry, find the molecular shape. So you have to have the lowest structure to start with in order to get your geometry and shape. So to get those, we need to get the static number, the SN. So the static number is the total number of atoms bonded to the central. So I go over here and say, okay, my central atom is carbon. So the total number of atoms that are bonded to the central are two atoms, right? So that is going to be two. Plus the lone pair. What is the lone pair? The lone pair on the central atom. I don't care about the edges there. I don't care about the oxygens, but I care about the central atom because when you find the geometry, when you find the shape, that is for the central atom. So the static number is for the central atom. I have no lone pairs, so that is going to be 0. So the lone pair here is going to be equal to 0. So the steric number is going to be equal to 2 and the lone pair is going to be equal to 0. So after you do this, what we're going to do over here is there is on eCampus a VASPER table. And again, you're not memorizing this, you guys. You're just going to bring it with you. This is the formula for the steric number, which is called electron domain. And this is the column for the static number. So we got a static number of 2 and a lone pair of 0. So we are here, okay? So a static number of 2 and a lone pair of 0. A static number of 2 and a lone pair of 0. Let me erase that. So here you go. Static number of 2 and a lone pair of 0. You can read the geometry and you can read the shape. Okay, so the geometry is linear, the shape is linear in here, and the bond angle is 180 degrees. Of course, if it is linear, then this means that it is a line, and the line has a bond angle of 180 degrees. So you come over here and say, okay, my bond angle is between the bonds of the central atom and the atoms that are connected to it. So this is the bond angle, and the bond angle is 180 degrees. My molecular geometry is going to be linear and my shape is going to be linear. What's the difference between the shape and the geometry? There's no difference if there is no lone pair. The shape changes whenever there is a lone pair on the central atom. So whenever there is a lone pair on the central atom, then it's called a shape. And the shape it changes because lone pairs they tend to squish the bonds, so the bond angle will be less than what's supposed to be. Right now there is no bond lone pairs, so the bond angle is going to be 180 degrees. Okay, this is how you use the table. So there are a lot of examples in there because there's a lot of different static number. So again, the molecular geometry, this is the geometry of the central atom. The molecular shape is the arrangement of the groups around the central atom, including the lone pair. So if there's any lone pair on the central atom, then the geometry will be different than the shape. Shape will be completely different in there. Let's have another example. HCl. Okay. By the way, let me go up there. All of these bonds that you see, these are covalent bonds. These are two nonmetals in there, so these are covalent bonds. HCl. So again, you go ahead and you draw the lowest structure, get your valence electrons to draw the lowest structure. Make sure that the nitrogen is a zero charge. This is why I had to make it 3 bonds in the lone pair. Look at the formal charge table. Nitrogen needs to be 3 bonds and a lone pair. So that's why I stacked these 3 bonds on top of each other in there. Now my central atom. The central atom is where? The central atom is not the nitrogen, you guys. The central atom here is the carbon, because carbon is less electronegative than nitrogen. Okay. Um, and by the way, it's HCN. So the H is connected to the carbon, and the carbon is connected to the nitrogen. So the carbon is the central element in there. So the steric number is the number of atoms bonded to the central. So I do have a hydrogen and I do have a nitrogen in there. So that is going to be equal to 2 plus. Is there any lone pair on the carbon? There is none. So that is going to be 0. So the steric number is going to be 2 and the lone pair is going to be 0. So the geometry and the shape is going to be similar to the top one. Check the table. So the geometry is going to be linear, the shape is going to be linear, and the bond angle is going to be 180 degrees. And again, the bond angle is the angle between the bonds, between the central atom and the atoms that are connected to it. So that is 180 degrees. This is whenever I have 2 groups around the central atom. Now, I can have 3 groups around the central atom, something like SO2 in there. So calculate your valence electrons for the structure. Go ahead and put the structure in here, and this is what I have. Oxygen is octet, sulfur is octet, and this oxygen is, let's see, this one over here is not octet. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and I am missing 2 electrons in there. Okay, so please go ahead and add those 2 electrons. And this is going to be all of that. It's going to be um, octet. Now, with respect to the charges, the oxygen is a negative charge. This sulfur over here needs to be plus a charge. Let's go ahead and check that. The formal charge of the sulfur is equal to 6 minus half. 1, 2, 3, 4, 5, 6 minus 2. Okay, so it's equal to 6 minus 3 minus 2. So that is equal to 6 minus 5. So it's going to be equal to plus 1 in there. See, you easily can see there's something wrong because the oxygen, when it does one bond, it's a negative charge. So if this is a negative charge and the total charge here is 0, then definitely the sulfur needs to be positive just to balance that. Okay, so this is the Lewis structure. Once you draw your Lewis structure, you're going to get the steric number. So it is the number of atoms connected to the central. So your central here is sulfur. So the number of atoms are 2 oxygens there, plus the lone pair. Do you have a lone pair on the sulfur? Yes, I do. It's a lone pair. It's not electrons, it's a lone pair. So I have 1 lone pair. The lone pair is made up of 2 electrons, but I have 1 lone pair. So I would say 2 plus 1. Guys, not 2 plus 2, it's 2 plus 1. And the 1 here is 1 lone pair. The moment you have a lone pair on the central atom, your geometry is going to be different than the shape. And you're going to read it from the VSEPR table. So the lone pair is going to be 1. So what you're looking for is a steric number of 3 and the lone pair of 1. So we're going to go to the table. And the steric number of 3 and the lone pair of 1. So here's what you have. A steric number of 3 and the lone pair of 1. So your geometry is a trigonal planar. This is your geometry in there. And then your shape for the 1 is going to be bent. This is going to be the shape. See, the shape is different than the geometry. Why this shape is different than the geometry? Because you have lone pairs on the central atom. And those lone pairs are going to squish the bonds. So when you want to draw it, I did give an example, by the way, of how to draw these. So if it is bent, it's going to look like this, and the bond angle is going to be less than 120 degrees. If there's no lone pairs, the ideal angle is 120. But the moment you have lone pairs, then the angle is going to decrease for this one. So it's going to be less than 120 degrees. So we're going to go over here and we're going to say, okay, the molecular geometry for this structure is going to be a trigonal, planar, and the molecular shape is going to be bent. So now when I want to draw it, I'm just going to go ahead and draw it as a bent structure. So I'm going to draw it as a sulfur and two double bond oxygen here and then an oxygen in there just to draw it as a bent, because you cannot draw it as linear anymore. The bond angle is going to be less than 120 degrees. Show all your lone pairs. In this case, you can show the charges, no problem with that. And then you would say, okay, the bond angle here between the sulfur and the two oxygens is less than 120 degrees. So the bond angle is less than 120 degrees. So the idea here is that the moment there is lone pair on the central atom, the lone pair is going to squish the bonds. So the bond angle is going to be less than the ideal bond angle when there is no lone pairs. See what I'm saying? So this is going to be the geometry and the shape, and you have to show it as bent. You cannot show it as linear. When you draw the Lewis structure, you don't show molecular geometry or shape. But from the Lewis structure, once you deduce the geometry and shape, you have to draw it as such. And again, this you figure it out from the VSEPR table. Another example, CH2O. Okay, so we're going to go ahead, distribute the 12 valence electrons. One thing that I want to say here, carbon. Carbon is the unique element. Oxygen is another unique element, but carbon is less electronegative. Okay, so carbon is less electronegative, so carbon is going to be in the center in there. So the carbon now is connected to the two hydrogens and the oxygen. Guys, there is no other way. There is no other way in there because you cannot have hydrogen in the center. So you cannot say, okay, I have a hydrogen here and I have an oxygen there. And then I have another hydrogen here. This is wrong. This is wrong. So whenever you have a carbon, a hydrogen, hydrogens, you keep them next to the carbon, and you want to reserve them next to the carbon because you know that carbon needs all of these bonds to make four bonds, all of these hydrogens to make four bonds there. And carbon as well needs to be connected to the oxygen because we're running out of groups. We need four groups around the carbon, and we only have three. So definitely the oxygen is going to be a double bond with the carbon. Once I do this, then I look at the central atom and I say, okay, let's calculate the steric number. The steric number for the carbon is the number of atoms connected to the central, and it is going to be 3, plus the lone pair on the carbon, that is a 0. So the lone pair is going to be a 0. So the steric number is a 3, and the lone pair is a 0. Okay? Steric number 3, lone pair is a 0. So now I go ahead and I look at the VSEPR table. Steric number 3, lone pair 0, then the geometry and the shape are the same. And I'm just going to go ahead and draw it as a triangle. Okay? Draw it as triangle, and the bond angle is going to be 180 degrees. So I'm just going to draw it as a triangle in there. I can draw it like this as well. Okay, whatever you want. Just make sure that it is kind of like a triangle in there, and the bond angle is 120. This is 120, and this is 120 degrees. So each one of those is 120 degrees. And the molecular geometry and shape, this is trigonal, planar, same thing, and the bond angle is 120 degrees. Okay, we're going to do the same thing for BF3. BF3 as well. Draw its valence electrons, put that in the steric number. There is no lone pair on the boron, so the steric number of the boron is going to be 3 plus 0, so it's going to be 3. The lone pair is going to be 0, so it's going to be 3, 0. Geometry and shape is going to be the same as above, so trigonal, planar for both. So trigonal, planar, and you're going to show it as a triangle with 120 degree bond angle. Okay? 4 groups around the central atom. The four groups around the central atom, this is a criteria for the carbon because carbon always forms four bonds. So it does have four groups around the central atom. Example CH4. You look at the carbon. This is static number 4 because it does have four groups around it. Plus 0. So the 0 is going to be no lone pairs on the carbon. So this is why it is a 0. And we're looking at 4-0. 4-0 from the table. Please put the table in front of you, you guys. So 4-0, this is tetrahedral. And the geometry and the shape is going to be the same because the static number is a 0. Guys, tetrahedral is drawn like this. It's two bonds in plane, one bond which is in front, we show it as a wedge. And then the one which is a dash, we show it to be behind. So two bonds in plane, one bond in front, the other one is behind. And the bond angle between the two lines in plane is 109.5. You can simply, this is how you show it. This is how a tetrahedral structure looks like. And this is whenever you have two bonds in plane, the bond angle is the 109.5. You can draw a tetrahedral carbon any way you want. Any way you want in there, because you can simply rotate that tetrahedral carbon as long as you have two bonds in plane. So each one of these structures have two bonds in plane, one behind and the other one is in front for all of them. So two bonds in plane, behind and front, two bonds in plane, this one is behind, this one is in front. Then this is supposed to be a tetrahedral angle, and you measure the bond angle between the two lines in plane to be 109.5 degrees. This is the ideal bond angle for a tetrahedral geometry with a zero lone pair. Now, ammonia. Ammonia is, you have this Lewis structure in there for them. Actually, this one is the Lewis structure, not this, this. Okay, so this is the Lewis structure of ammonia, distributing the 8 electrons around the nitrogen. So you're going to have a lone pair here. So for the ammonia, if I'm looking at the static number for the ammonia, let's write it down. So the static number here is equal to the number of atoms connected to the central. So this is the central. The number of atoms are 1, 2, and 3. So that is going to be 3. Plus the lone pair, I do have here one lone pair. So that is going to be plus 1. So the static number here is going to be 4. And the lone pair is going to be 1. So static number 4, lone pair 1. So we're going to come here. Static number 4, lone pair 1. Then see, the geometry is tetrahedral, but the shape changed now. The shape is trigonal pyramidal. And let me go ahead and change that. The trigonal pyramidal always looks like this. So an example, you have the central atom, and then you have one bond behind, the another one in front, and then the other one in plane. Okay, and for the NH3, you do have the two lone pairs on the nitrogen, and these are the hydrogens in there. The bond angle is normally the angle between the bond in front and the bond in plane. So this is the bond angle here, and the bond angle is going to be less than the ideal because after all, this one is a tetrahedral geometry. And tetrahedral has to be 109.5, but if there's a lone pair, then the angle will be less than 109.5. Okay? So this is how you draw trigonal pyramidal. It's like a pyramid and a triangle at the same time. So you have your central atom, and this is making a pyramid structure there. Okay? So it's making a pyramid structure. One bond behind, the other one is in front, and the other one is in plane. And the bond angle for this one is going to be less than 109. It's normally 107. You don't know, you need to know this number, you know. You can say it's just 109.5, less than 109.5. But precisely it is 107 degrees. So the geometry is tetrahedral, shape is a trigonal pyramidal in there, and the bond angle is going to be 107 degrees, or you can say less than 109.5. Water. Water here does have valence electrons. So you complete your valence electrons, which is 8 valence electrons there. Okay, distribute, and then we're gonna go ahead and calculate the static number for the water. So you look at the central atom, and it's connected to two hydrogens. So that is going to be 2. Plus, how many lone pairs do you have? 2 lone pairs. You have one lone pair here, one lone pair here. So that is 2. So this is 4, static number 4, and the lone pair is equal to 2. So we're looking at the Vasper table of 4 and 2 columns. So 4 and 2. So we are here. We are here. Okay. So 4 and 2. So it's still tetrahedral, but now the shape is bent. You see it? And this is how you draw the bent shape in there. And now the bond angle is even less than 109.5, you guys, because it is 2 lone pairs, not one. It's even like the bonds here are squished more. So the more the lone pairs are around the central atom, the lower is the bond angle in there. So this is why I showed it as a bent structure, and the bond angle here is 109.5. Actually, it is 105 degrees. It's less than 107. Or you can say it's less than 109.5. Okay, so that is going to be 105 degrees. And you need to show it as a bent structure. So you no longer need to should write it as a linear one. You have to show it based on its bond angle in there and based on its shape, which is bent. Carbon tetrachloride. So these are all examples of tetrahedral geometry. So you do have a carbon, around it there is 4 chlorines in there. Please show it as a tetrahedral. This is 4, 0. So the static number for this one is equal to 4 and 0. This is the static number, 4 plus 0. So that is equal to 4, and the lone pair is equal to 0. We go to the table, and we are working with 4, and we are working with 0. So your geometry is tetrahedral and your shape is tetrahedral, and you have to draw it like that. And your bond angle is going to be 109.5 between the two lines in play. So your bond angle here is equal to 109.5. Okay, we still have the fiber groups and the 6 groups around the central. So whenever you have fiber groups around the central atom, then the shape is going to look like this. What do we call it? We call it a trigonal bipyramidal. I did put the shape in a 3D, and I'm showing it to you as a stick model in there just to see that you do have two, actually, you do have 1, 2, and 3. So you do have three groups in there around the central atom that belongs to one plane, and another two groups in here that belong to another plane. So you do have here two different planes, and this means that you have two bond angles. You have the 90 and you have the 120. These are the two bond angles there. Let's have an example. PCl5. You need to have a trigonal bipyramidal, which is 5 groups, right, around the central atom. You need to have 5 groups around the central atom there. So PCl5 is a good example in here. So what we have is calculate your valence electrons. This is 40, and then we're going to go ahead and draw its Lewis structure. So we have a phosphorus in there, and we're going to put those 5. This is 1, 2, 3, 4, and 5. That's it. So you have the 5, so you have the chlorine, 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 and the chlorine. And then you're going to put all the valence electrons in here. Just make sure that you cover all the 40. If there's any left over, it goes on the phosphorus. But here there is no leftover, so this is going to be my Lewis structure. Okay. Now, static number. So to calculate the static number for this one, the static number is going to be number of atoms connected to the central, and the number of atoms here is 5, because you have 5 chlorines, and you have no lone pairs, so it's going to be 5 plus 0, so it's going to be 5. The lone pair is going to be 0. So I come over here, and I say, okay, 5, 0, then the geometry and the shape are similar. It's a trigonal bipyramidal, and this is how it's going to look like. And we have two bond angles. We have bond angle which is 90 and another bond angle which is 20 degrees, 120 degrees. Okay, so this is again how you draw it in there. You don't have to memorize anything, you have the table. So the molecular geometry for this one is going to be trigonal bipyramidal, bipyramidal, and the shape is going to be the same. SF4, in here, even though it seems like I have 4 atoms around the sulfur, but always remember that you might have also an additional lone pair on the sulfur that will make it 5 groups, as in this case over here. So in this case, I do have 34 valence electrons. We go ahead and we distribute those 34 valence electrons. We can draw this is 1, 2, 3, and 4. So this is fluorine. I'm just drawing the lowest structure right now. Here you go. We will have a lone pair on the sulfur. Here you go. So this is the lone pair on the sulfur. So what I just drew is the lowest structure. And then you calculate the static number, which is 4 plus 1. So that is going to be 5. And lone pair is equal to 1. So we're looking at 5, 1. So you go to the table because you want to know how to draw it, right? So you go to the table and say, okay, static number 5, lone pair of 1. The geometry is trigonal bipyramidal, but the shape is a seesaw. How do we draw the seesaw? Like this. This is how we draw the seesaw. The seesaw needs to have 2 bonds in plane, one behind and the other one is in front, and you have the lone pair on the, of course, on the central atom. The bond angle, you have 2 bond angles in there between the fluorines and between the other 2 fluorines. So it's going to be less than 90 and less than 120 because of the presence of 1 lone pair. So it's going to be less than the ideal one. Okay, so we're going to end up having so you have the 90. So this is going to be your 90. This is going to be your 90 here, and then this is going to be your 120. It's going to be your 120 in there. Sorry. So it's going to be the 90, and this over here is going to be your 120. Okay. Between those two, it's going to be the 120, and between those two, it's going to be the 90 degrees. The molecular geometry and shape for this one, we said that the molecular geometry is the trigonal bipyramidal. So this one is the trigonal bipyramidal, and the shape is going to be a seesaw. Seesaw has a bond angle less than 90 degrees, and it does have a bond angle less than 120 degrees. Another example here is whenever you have 2 lone pairs. So this is still a static number of 5. The Cl, this is a chlorine. So you have a ClF3. If you distribute the valence electrons, you'll see that you're going to have 2 lone pairs on the chlorine in there. I am not showing the lone pairs here, so please go ahead and show the lone pairs on the fluorine as well. Okay, so we are looking at a valence at a static number of 3 plus 2, so it's going to be 5, and the lone pair equal to 2. This is what we're looking for. So 5, 2. So you go 5, you go 2, and this is going to be a T-shaped. The T shape is going to look like this, you guys, and there is only one bond angle here, which is less than 90 degrees. So the geometry is the trigonal bipyramidal, and the shape is a T shape there. So the shape here is a T shape, and the geometry is a trigonal bipyramidal. Okay, and the bond angle is going to be less than 90 degrees. So the bond angle is going to be less than 90 degrees. I3 is the same thing, and this is an example of a static number of 5 and a lone pair of 3. So you have 2 plus 3, that is 5, and the lone pair equal to 3. For I3 minus, I have 3 lone pairs. There you go. See? three lone pairs, and five atoms and lone pairs. So 3 plus 2, this is 5. This is static number. So 5 to 3, if you look at the table, 5 to 3, this is going to be linear. So the bond angle has to be linear, means 180 degrees. Geometry is diagonal bipyramidal. The shape is going to differ, and the shape is going to be linear. Now for the six groups around the central atom. So you have your central atom, you have six groups around it. So this is going to be an octahedral shape and octahedral geometry if there is no lone pairs on the central atom. The bond angle is going to be 90 degrees. So let's have an example of this. For example, SF6. We did this before. So you just go ahead and calculate the valence electrons for the SF6 to draw its Lewis structure. Once you draw its Lewis structure, go ahead and calculate its static number, which is the number of atoms connected to the central. Your central is sulfur. The number of atoms are actually six of them, three here and the three there. It's six of them. So that is going to be six plus no lone pairs on the sulfur. So the static number is 6, and the lone pair, this is going to be 0. So you go to the table because you want to know how to draw it, right? So you go 6, 0, and this one is going to be an octahedral, and the shape is going to be an octahedral as well. And this is how you draw it. So you need to have two bonds in plane, two bonds behind, two bonds in front. This is how you draw it. Draw it exactly as you see it. So I'm drawing it as I'm seeing it there, just to put the geometry, put the shape, and put the bond angle. Now, another example is SbCl5 2 minus. What is this? This is pay attention, it's 2 minus. So when you calculate your valence electrons, you have to add 2 electrons there. So if you calculate your valence electrons and just distribute them, and you're going to see that you have a lone pair, which is on the central atom left. I'm not showing any of the lone pairs, but just go ahead and write them down. Okay. Same thing for the fluorines up there. I didn't show the lone pairs. Just go ahead and write them down. So calculate your static number here. The static number is the number of atoms connected to the central. So I do have 5 chlorines, so this is going to be 5. Plus, there is one lone pair, so I'm talking about 6 static number, and the lone pair now is equal to 1. So I go over here to the table, and okay. So static number 6, lone pair 1. The geometry is octahedral, and the shape is a square pyramidal, and this is how you draw it. This is how you draw the square pyramidal. You do have one bond in plane, and then 2 are behind and 2 are in front. The bond angle is going to be less than 90 degrees. Okay, so the bond angle there is going to be less than 90 degrees between the chlorines. Just write down the geometry and the shape for that.